Hello friends, today we will talk about the limit superior and limit inferior of the real sequences. So you are well familiar with the supremum of bounded set, infimum of bounded set. If given set, subset A of real numbers is bounded above, then there exists some real number u such that every number x in A is less equal to u. Then that u is called as upper bound of that set. Among all upper bounds, the smallest upper bound is known as the least upper bound of the set. So every number in given set is always less equal supremum or least upper bound of the set. Similarly for infimum or greatest lower bound. So, and if given set is not bounded above, given set A is not bounded above, then we will denote supremum of that set A to be infinity. Supremum of A is equal to infinity. If given set is not bounded below, then we will denote infimum of that set to be minus infinity. So likewise that, if Sn is a real sequence, if it is not bounded above set, then supremum for Sn plus 1 must not exist. As that set is not bounded above. Sequence is not bounded above means as intending to infinity, terms of that sequence goes on increasing. That sequence is not increasing, but for any positive integer n, you will get Sn such that Sn is greater than m for any n greater equal to n naught. So, supremum of Sn plus 1 is equal to infinity for any n positive integer n. In that case, we will denote the limsup of Sn is equal to infinity. Limsup of Sn is equal to infinity. Now, if Sn is bounded above sequence, then supremum of Sn plus 1 and so on must exist. And then you can observe Sn plus 1, Sn plus 2 and so on. This is subset of Sn plus 1, Sn plus 2 over the subset, supremum decreases. Over the subset, supremum decreases while infimum increases. Suppose this is this Sn plus 1 lies here and this contains one less term than this, means this set is here. This set is here. Means here, this is the supremum here. This becomes supremum for this set. So over the subset, supremum decreases and over subset, infimum decreases. Infimum is here for the superset and for its subset, infimum is here. Means supremum decreases over subset while infimum increases over the subsets. Is it clear? So by that relation, Mn plus 1 is always less equal to Mn means sequence of these supremums is decreasing sequence. If Sn is bounded above sequence. Now if this Mn is not bounded below, then that Mn must approaches to us minus infinity. If it is not bounded below sequence, then Mn approaches to us minus infinity means supremum of Sn plus 1 that approaches to us minus infinity, and in that case we will denote limsup of Sn it to be minus infinity. If Mn is bounded below sequence, every decreasing bounded below sequence is convergent and converges to infimum of that sequence. Infimum of Mn's. And then in that case, limsup of Sn is limit n tends to infinity of Mn exist. And this is finite number. This is finite number. On same line, now we'll talk about the limInf. LimInf. Okay. Similarly, if Sn is a real sequence, then if Sn is not bounded below, means infimum doesn't exist. In that case, Mn is equal to infimum is minus infinity for all n. For all n. In this case, we will denote liminf of Sn is equal to minus infinity. If Sn is bounded below sequence, Sn is bounded below, then Mn is equal to infimum of Sn plus 1 dot dot must exist. Moreover, your Mn plus 1 is greater or equal Mn. Over the subset, infimum increases. Over the subset, infimum increases. So we'll get Mn is non-decreasing sequence, means increasing sequence. So Mn, if Mn is bounded above sequence, above, then it is convergent. Then it is increasing and bounded above, therefore it is convergent, and in this case liminf of Sn is equal to limit of small mn must exist. Limit of small mn must exist. If that mn sequence of infimums is not bounded above, if this mn is not bounded above sequence, it goes on increasing, infimums of Sn plus 1 goes on increasing, then liminf of Sn is equal to limit of Mn is infinity. Is infinity. Is it clear? So, these are the definitions of limit superior of sequence and limit inferior of sequence. Okay. Now, we'll take the theoretical part. Examples. Write limsup and liminf. Sn. Okay. So, Sn, limsup Sn, limin Sn. So, first one, if I take 1 upon n sequence, 1 upon n sequence, then 1 by n itself is decreasing sequence. It is bounded below as well as bounded above sequence. Bounded below, bounded above sequence. Okay. So if I take supremum, okay, what is m1 here? m1 is equal to 1, m2 is equal to half, and so on. Mn is equal to 1 by n. This tends to 0. Now what is the small mn? Small mn is 0 for all n. 0 for all n, and therefore mn tends to 0 as n tends to infinity. As n tends to infinity. If I take minus 1 raised to n sequence, n is equal to 1 to infinity, then your mn is equal to 1 tends to 1 as n tends to infinity. Means limsup of Sn is 1. Therefore, limsup Sn is 0. Okay. And here limsup of Sn is 1. Mn is equal to minus 1, which tends to minus 1. as n tends to infinity. And therefore, liminf Sn is minus 1. Here these two are not equal. These two are not equal. Now if I take say n is equal to 1 to infinity, this sequence, then this is infinity. This is infinity. Limsup of Sn, as it is not bounded above, it is infinity. Small mn is equal to n tends to infinity, as n tends to infinity, as n tending to infinity. Okay. And therefore liminf of Sn is also infinity. Fourth one, if I take minus n sequence, n is equal to 1 to infinity say, then capital Mn is minus n which tends to minus infinity, as n tends to infinity, and therefore limsup of Sn is minus infinity, and this is infinite minus infinity. As it is not bounded below sequence, sequence is not bounded below, so we'll get this. Is it clear? Now take the theorem. If Sn is convergent sequence, if Sn is convergent sequence, such that limit of Sn is L, then limsup of Sn is equal to liminf of Sn is equal to M. Okay. So since limit of Sn is equal to L, n tends to infinity, therefore for given epsilon greater than 0, there exists positive integer n0 such that mod of Sn minus L is less than epsilon for any n greater or equal n0. Therefore, L minus epsilon is less than Sn less than L plus epsilon for any n greater or equal n0. This is one. This implies L plus epsilon is upper bound for Sn, Sn plus 1 and so on. And L minus epsilon, that is number less than L, is not upper bound, for Sn, Sn plus 1, okay, for any n greater or equal n0. Epsilon to be any number, even though it is too small, L minus epsilon is not upper bound for this set. For this implies L minus epsilon is less than least upper bound of the set Sn, Sn plus 1 and so on. This is less equal L plus epsilon for any n greater or equal n0. It may happen that supremum approaches towards L plus epsilon, but epsilon is again too small. Epsilon is very, very small. It is negligible. Okay. This implies mod of least upper bound of the set Sn, Sn plus 1 and so on minus L less equal epsilon for any n greater equal n naught. Right? And therefore, and this is nothing but mod mn minus L is less than equal to epsilon for any n greater equal n naught. Therefore, limit n tends to infinity of mn is L. For given epsilon greater than 0, there exists n naught. Okay. And therefore, limsup of Sn is L. Again from 1, L minus epsilon is lower bound for Sn, Sm plus 1 and so on, n greater equal n naught, while L plus epsilon is not lower bound for Sn, Sm plus 1 and so on for n greater equal n naught. What this implies is epsilon is very, very small. For any epsilon greater than 0, it is true. Means any number greater equal L greater than L is never lower bound, because choice of epsilon is arbitrary. This implies L minus epsilon is less equal greatest lower bound of set Sn, Sm plus 1 and so on is less than L plus epsilon for any n greater equal n naught. And therefore, mod of greatest lower bound Sn, Sm plus 1 and so on minus L less than epsilon less equal epsilon for any n greater equal n naught. Right? For any n greater equal n naught. This implies limit n tends to infinity of mn is equal to L. This is your mn, right? And therefore, liminf of Sn is equal to L. Thus, the result is proved. From A and B, the result is proved. Or theorem is proved. Converse of this theorem is also true. If Sn is bounded sequence such that limsup of Sn is equal to liminf of Sn, then limit of Sn must be equal to that value. Okay. So, converse. Next theorem, converse. If Sn is bounded sequence such that limsup of Sn is equal to liminf of Sn is equal to L, then limit of Sn is also L. So as this is a Fano leaf condition, so by using this result, if for given sequence limsup not equal to limin, then that sequence is not convergent. Okay. So from 1, for given epsilon greater than 0, there exist positive integers n1 n2 greater than n1 n2 such that mod of least upper bound of Sn, Sn plus 1 and so on minus L less than epsilon n greater equal n1 and greatest lower bound of Sn, Sn plus 1 and so on minus L is less than epsilon for any n greater equal n1, n2, which implies L minus epsilon is less than L minus epsilon is less than Sn least upper bound of set Sn, Sn plus 1 and so on less than L plus epsilon n greater equal n1 and L plus L minus epsilon less than greatest lower bound of Sn, Sn plus 1 and so on less than L plus epsilon for any n greater equal n naught is equal to maximum of n1 n2. n1 n2. Now least upper bound of this set is less than L plus epsilon. Okay, this implies Sn is less than L plus epsilon for every n greater equal n naught and L minus epsilon is also less than Sn for every n greater equal n naught. Okay. So this is 2, this is 3. This is from 2, this is from 3. From 2, least upper bound of this set is less than L plus epsilon, means every term in this set must be less than L plus epsilon. Greatest lower bound is greater than L minus epsilon, means every term in this set must be greater than L minus epsilon. Because if some number is less than L minus epsilon, then that term is less than this. That gives us contradiction to this. Okay. So this implies L minus epsilon less than Sn less than L plus epsilon for any n greater equal n naught. And therefore mod of Sn minus L less than epsilon for any n greater equal n naught. So what we proved, okay, thus or this implies for given epsilon greater than 0, there exists n naught is maximum of this, such that mod Sn minus L less than epsilon. Therefore, limit n tends to infinity of Sn is equal to L. Sn is equal to L. If I take the sequence minus 1 raised to n equal to 1 to infinity, then liminf of Sn is minus 1, limsup of Sn is 1, that two are not equal. Therefore, by this if and only if condition, given sequence Sn must be divergent. Sn must be divergent. Is it clear? So, with the discussion, we will stop our today's session here. Thanks for listening lecture carefully. Bye bye.